Okay, thanks a lot for the invitation and to the organizers for organizing this fantastic conference. I'm having a lot of fun so far. I want to tell you about this work that we recently put out with my student Jonah and collaborator Maria Derda from Caltech, which are both fantastic. Maria might be here at some point. But yeah, my talk is about soft theorems. So just to remind you very quickly what a soft theorem is. So oftentimes when we have a scattering amplitude and we have a massless particle, we can take the momentum of that particle to be soft, so very small. And typically there's some universal behavior, which often takes the form of some operator or some number multiplying the amplitude without that soft particle. And so the earliest examples of that are things like the Adler zero in Carl perturbation theory. So if we take a soft pion in low energy QCD, then the amplitude with that extra pion will just vanish as with the soft momentum of the pion. And the low soft photon theorem, which is very famous, that if we take a kind of a soft photon, there's this universal soft factor that depends on the charges of the massive particle, of the charges of the various particles in the process, polarization of the photon, the momentum of the photon, and the momenta of the particle. Okay, so there's many perspectives of what these soft theorems mean. So for instance, some people say that they're a consequence of symmetry, of geometry. We saw in Andres' talk. I also gave a talk about this a couple of years ago. If you come from the EFT community, maybe you say that soft theorems are just a statement about kind of EFT, that they're just kind of the leading low energy operators that you can write in a EFT for the soft modes. But I think generally the connections between these different perspectives are largely unexplored. And for me personally, it always bugged me that explaining soft scalar and soft photon theorems using symmetry arguments require invoking very different ideas. Like in one case, it's things like spontaneously broken chiral symmetry. The other one is things like asymptotic symmetries, something very Lorentzian. But fortunately, in the last decade or so, there's been kind of a great expansion in what we understand as symmetry in various directions. If you haven't been living under a rock, probably you've been hearing some of these words either or reading them in abstracts on the archive, things like higher form symmetry, higher group symmetry, categorical symmetry, or non-invertible symmetries. Okay, so I won't explain what all of these things are, but some of them have found applications in amplitudes, but not so many. So there's a couple papers on the topic of these non-invertible symmetries. I think Lucia might tell us about this later this week. But today I'm going to try to argue that this language of this higher symmetry can provide kind of a unified perspective on soft photons and pion theorems, and also it suggests new soft theorems and new structures. Okay, so this is the outline of the talk. I'm very quickly review our understanding of soft pions from symmetry breaking, and then I'll explain how one can explain soft photons very much in the same language, and then introduce a new soft theorem that has to do with a structure called the two group, which I'll explain. Okay, so let's start with soft pions. So the typical setup is spontaneously broken symmetry, right? So we have some local operator in some quantum field theory that picks up a vacuum expectation value, and this is charged under some symmetry G, which is broken down to H, some subgroup. And okay, so if these are continuous symmetry, typically we have some algebra that looks like this. So the unbroken subgroup is closed, but then there's these broken generators X that transform in some representation of G, and they also close onto T. And the most famous consequence of this of symmetry breaking is the existence of a massless particle. Okay, so that's a very sad consequence. So essentially, Goldstone's theorem. A quick way to see it is that if I have this charge operator, if I look at the word identity in the presence of the broken current, this is going to have a contact term, which multiplied by the charge of the operator. So this is for U1 symmetry for simplicity, which means that this correlation function has to have power law decay, which means that there has to be a massless particle somewhere. Okay, this is not the usual Lorentzian proof, but that gives you the intuition. And we can write a theory for the fluctuations of this VEV, which are these Goldstone bosons. Okay, so the massless particles you can think of as the fluctuations of this vacuum expectation value. So the most famous example is pions. So the consequence of Goldstone's theorem is that the broken current has an overlap with a one particle state. So it can create a single pion. So there's this kind of matrix element, which tells you that the current is linear in this goldstone, and that hence the goldstone shifts under the symmetry. Okay, so this broken symmetry typically appears as this nonlinear realized symmetry, which is a shift symmetry in the EFT of these particles. Okay, and the most famous example is just QCD in the chiral limit, so massless QCD, where we have kind of left and right moving like chiral symmetries acting on the left-handed and right-handed quarks, which get broken down to the vector kind of diagonal subgroup. And it's a quark bilinear that picks up a wave, and okay, the rest is history. We know very well how to write an EFT for these pions and how to compute amplitudes. So this is the famous nonlinear sigma model. Okay, so one of the consequences of this, when you now think instead of just one particle state overlap of the current with a multi-particle state, is a Adler zero. The proof is very easy. There's a one pion pole. There's a remainder, which is smooth as Q goes to 0. And then conservation of the current relates these two things, which means that when you take soft Q, the momentum of the pion, then the rest needs to vanish with the power of Q. Okay, so, and I'm showing the proof because you'll see that for soft photons, there's something very similar. Okay, and I won't review the proof, but you can also look at the now 2-point function of the currents. So now you have a non-abelian word identity, and then that actually leads by similar current algebra arguments to a double soft theorem. So for instance, the leading double soft theorem knows about the commutator of these broken generators. It's pretty famous, and it's also less well known, but there's a subleading one that has like the usual form with angular momentum operator and other pieces. And we'll see that this will get modified when we add some interesting structure. Okay, so this is old stuff. So now let's talk about photons. And first, I want to tell you about this idea of one-form symmetry. Maybe some of you are familiar with it, but it's okay. So now instead of having a conserved current, which is a rank 1 tensor, we have a kind of rank 2 tensor. So the charges live on codimension 2 surfaces. So for instance, an example we'll see later is the electric flux. One can think of as this kind of thing, the integral of the field strength, right? But because they're codimension 2, these charges, the symmetries act on extended operators. So for instance, they can act on a Wilson line. So if I have a Wilson line or some line operator, I wrap it with this charge, and then that will give me a phase. Okay, so they cannot act on local operators because this is like higher codimension. So it commutes with anything which is supported on a point. Okay? But also because they're higher codimension, these typically are abelian, because I can always deform this configuration. So the charge being conserved means that it only depends on deformation classes of the surface, just like usual charges. We can move up and down in time. So this one, I can just exchange these two symmetry defects, and I get the same result. Okay, so these are at most U1 symmetries, which act on extended operators. And they also have word identities that tell you that line operators are charged, which look like this. Okay, so this delta function here is kind of a codimension 1 delta function. This is completely analogous to the usual word identity when you have a charged local operator. And this delta function you can just think of as a delta function on the word line of this line operator. Okay, so we have some parameterization of this line, and it's just a delta function that if I integrate against any surface that intersects this line, will give me 1. Okay? So I'm showing you the expression because we'll use it in a second. And these symmetries can also be spontaneously broken. So for instance, this famous perimeter law of Wilson lines in this language is interpreted as a statement of breaking of this one-form symmetry, spontaneous breaking. Because the idea is that this perimeter law, I can always redefine away the perimeter by adding a counter term on the line, which means that actually this Wilson line expectation value just goes to a constant when it becomes large. So since it's a constant, this line has a web, so the symmetry is broken. And also, this tells you that there has to be some massless particle somewhere by the same argument. So now we have some power law correlation, which tells you that there has to be a massless particle. And indeed, the photon can be thought of as a goldstone for this kind of symmetry. I'll show you an example. And same as before, so I show you that the pion was a fluctuation of the web of the kind of order parameter that breaks the symmetry. The same is true, and you can think of that as the reason why we write the Wilson line as an exponential of the photon. Okay, so the simplest example is the photon. So notice that these equations are very similar to the ones for pions. So we do have some current here, which will be the field strength, for instance, of the photon, and it has a overlap with a one particle state, which looks like this, which also means that the current is linear in this photon. So you see here that is the field strength plus possibly some corrections, which implements a shift symmetry on the photon. So the idea is that the symmetry takes the photon and shifts it by a form which is close but not exact. Okay, so this is not a gauge transformation. So lambda is not d of something, right? It's a non-trivial one form. Of course, this is a symmetry if you write everything in terms of field strength, so it's very natural. Okay, so an example is just pre-Maxwell theory can be thought of as a theory of symmetry breaking. So we have this one-form symmetry, which is called electric, and which is just the electric flux. There's also the magnetic flux, which is also conserved by the Bianchi identity. And then you can think of the theory of symmetry breaking of those symmetries, which are one-form symmetries down to nothing. Okay, so there's a precise sense in which the photon is a Gaussian boson. Okay, but typically when we try to understand the Weinberg or like the low soft-photon theorem in this language, there's an issue, which is that once we add charged particles, this breaks this symmetry. Okay, so one way to think about it is that the shift symmetry is broken if I have an explicit photon field, like in a covariant derivative. But physically, what's happening is, okay, now there's a current on the right-hand side of Maxwell's equation, so this electric flux is not conserved, and there's two things that can happen. Now, Wilson lights can end on charges, okay, so they cannot have a non-trivial flux, and also they can be screened. So you can have a Wilson line, which is like the Ward line of some very heavy charged particle, but then there can be a cloud of, say, electron and positrons floating around it that screen its electric charge as I try to measure the flux for infinity. Okay, so charges just break this symmetry. So, and this typically meant that it's hard to interpret this soft-photon theorem using this language. But notice that these symmetries are robust in the sense that even though if I broke the symmetry explicitly by adding this charged matter, the photon remains massless. This is unlike other Gaussians for ordinary symmetries. So for instance, the pion, once we add the quark masses to the QCD Lagrangian, it becomes a pseudo-Gaussian and it becomes massive. Okay, but since these one-form symmetries act only on extended operators, I cannot add any local operator to my Lagrangian that will break it. So for instance, the photon here, even though the symmetry is broken, it remains massless. Okay, so they're like stronger than other symmetries. And also typically when they emerge as exact symmetries for the same reason, because I cannot write any operator that breaks it. And we'll see an example. Okay, okay, let me just comment that the magnetic symmetry is still unbroken when we have this, because the Bianchi identity is still true if we don't have model. Okay, so there's two ways that we can recover this symmetry. So one is kind of boring, which is we can just integrate out the charged matter. So take the electron, integrate it out, a la Euler-Heisenberg. You're going to write an effective action for these photons. And then this obviously has the shift symmetry of the photon because it's written in terms of field strengths. Okay, and this one-form symmetry emerges as an exact symmetry of this theory. Okay, so we have that the current will be the electric kind of just the field strength plus some nonlinear corrections from the higher derivative terms. And this is kind of broken only non-perturbatively because I need to have effects that go like some power of the mass instead of 1 over the mass, which is the perturbative parameter in this EFT. Okay, and there is a soft photon theorem of kind of obvious in this theory because it's derivatively coupled, but which is not very interesting. But let's go through the proof to see that it's exactly analogous to the Adler zero. So we take this like 1-point function of the current, the form factor of the current in a multi-particle state. Now there's going to be a 1-photon pole plus a remainder, and then conservation as before is going to tell me that the amplitude with an extra photon is related to this remainder. So when I take the self-limit, I just get 0. Okay, so this is completely unsurprising that you see that at least it follows from this conservation of this current. Okay, just in the same way that the Adler zero follow. Okay, so the symmetries are abelian, so there is no interesting double soft like for pions. So we need to do something more interesting. So notice that another thing that we can do is that if we have this kind of soft photons interacting with matter, Typically, we mean that the momenta of the soft photon is much smaller than the mass of this charged matter. And in particular, it cannot kick off shell this particle. Okay, so it cannot, or another way of saying that is that it can never per-produce. So I can never have, like, if I have a soft photon with its energy is less than the mass, it doesn't have enough energy to produce like an electron-positron pair or something like that. Okay, and so in this limit, and we'll make this more precise, the amplitude actually at leading order in this limit will look something like a correlation of function of Wilson lines, where kind of the hard scattering process is just some local operator inserted at the origin, and then these kind of hard particles just stream out along fixed trajectories. Okay, so the paths are just straight lines which have the momenta of each one of these particles. Okay, so now we can apply this water identity of the one from symmetry. And I'll argue in a second that this symmetry is really emergent in this limit. And then if I apply now this water identity, because now I have charge operators, which are these line operators. Okay, so on the one hand, I would have the relation to the matrix element of the photon, just like in this slide. But then on the other hand, I can compute now the right-hand side of the water identity, which is these contact terms times the original correlation function. And then it turns out that the Fourier transform of these contact terms is precisely the Weinberg subfactor. Okay, so one can show that the soft photon theorem here appears just directly from the water identity of this one from symmetry in the presence of these line operators. Okay, so this is a bit fast. So what's going on here? So what's going on here is that in this limit, the right description is to use something like this, a heavy particle effective theory, where we separate kind of the positive and negative frequency modes. So we separate the particles and antiparticles. Okay, and then we focus only on excitations very close to the mass shell of the particle or of the antiparticle, and then we integrate out the rest. Okay, so we're integrating out the antiparticle. Okay, so this is what the kind of EFT looks like. And since we integrate out the antiparticle, there cannot be screening because this theory doesn't have particle production anymore. Okay, so per production is not it's completely thing in the UV. So indeed, one sees that this theory, one suspects that this theory will have this emergent shift symmetry, and one can make that very precise by just doing a field definition where we attach a line to each field. So this is a famous field definition that people do in say SAT literature, and this makes the shift symmetry manifest, because now every covariant derivative, which was the things that broke this one from symmetry, now can be written explicitly in terms of the field strength. Okay, so now this theory has a shift symmetry. So this heavy particle EFT has a one from symmetry, which justifies me using it to derive the Weinberg theorem. And also this field definition justifies this comment that the amplitude just looks like a correlation function of Wilson lines at a leading power. Okay, so this is the story about just soft photons. Okay, so far I haven't presented any new soft theorem. I just presented kind of an alternative perspective on the Weinberg's, the low soft photon theorem using this language of symmetry, and which makes it completely analogous to the soft pion theorem. Okay, but is there something that intertwines them? Okay, is there something more interesting, some new structure that we have learned from this recent literature that we can find some sort of new soft theorem? Okay, so I'm going to argue that the answer is yes. So there's something called a two group. So okay, stay with me. I will explain what this is. It's actually very simple. Okay, this is not simple, but I'm going to basically skip this slide. But the idea is that you can have something that you have like an ordinary symmetry G and a one from symmetry G, and they're intertwined in some way. So one way to think about it is if you take three charges of the zero from symmetry, in their intersection, there will be a charge for the one from symmetry. Okay, and you can also have to tell me how one of them acts on the other. So this is a mathematical structure that people have studied in the literature. You don't need to know all of these details, but you can think of it as a non-trivial extension of the zero form by the one form. So it's the closest thing to a non-abelian structure that we can have. So let me just show you the current algebra, which is much simpler. Okay, so for a continuous two group, the water identity now just has an extra term. Okay, so the idea is that we have this usual term for the non-abelian current algebra, so it's the usual contact term that knows about the structure constant. But now, because we have also a one-form current, which is a rank 2 tensor, then there's an extra contact term, which looks like a derivative of a delta function contracted with this current, and then some quantized constant. Okay. So this number here, kappa, is just some integer. Okay. So this is a rigid structure. It's not a parameter in the theory. This is really 1, 2, 3. Okay. So you can think of it as a new structure constant in the theory that tells you that somehow you can take a pair of pions or a pair of these ordinary symmetry currents and fuse them into one of these higher currents. Okay. And so we'll denote this symmetry like this. So we have, for instance, this will be a U1. It's always a U1. And then we have G, and then we have this product with kappa that reminds us that there's this intertwining. Okay. And so this suggests that there should be something new when we look at double soft pion theorems in the presence of this kind of symmetry, okay, that mixes up, say, pions, which would be the things associated to these currents, and photons, which are the things associated to these currents. And also, the fact that there's a derivative here suggests that it should appear at the subleading order. And we'll see that this is exactly what happens. Okay. So another way to think about this two group, which maybe makes it more familiar, is just kind of the fourth kind of triangle diagrams. So whenever we have anomalies and things like that in QFT, there's a lot of confusion because people call everything an anomaly, but there's different kinds. So for instance, if you have the usual triangle diagram with chiral fermions, where every corner is like a gauge current, then this is what's called a gauge anomaly, which is just an inconsistency of the theory. Okay. If you have 3 global currents in the corners of this triangle diagram, then this is not a problem. This just tells you that there's some interesting contact term in the 3-point function of these currents, but the symmetry is perfectly fine. Okay? So if I turn on background fields for this symmetry, then I will see that there's a right-hand side of the word identity. But if I don't turn on these background fields, then this current is conserved at separated points, which is what we require in quantum field theory. Okay, now if I make these Fs dynamical, so if I actually gauge some of these corners, then there's a celebrated Adler-Bell-Jaquib anomaly, which is when you have one global symmetry current and 2 gauge symmetry currents, where now what we have is the divergence of the current is an operator, which means that the current is not conserved. So this is actually the case of the anomaly where we really have a symmetry which is broken when you gauge something. And the two group is kind of the fourth option, where I have now 2 corners which are global symmetry and 1 corner which is gauged. Okay, so that means that if I don't turn on background fields, the current at each one of these corners will be perfectly conserved. But now if I turn on a background field, then I will see that there's some interesting contact term that mixes this current with the field strength which is attached to this corner, and that precisely corresponds to this thing here. So this thing here, you can think of this 2-point function of the current, you can get it by taking some extra kind of derivative with respect to the background field of this operator equation. Okay, so it's not something very exotic. I just need to find some triangle diagram where I have a special corner and I can gauge it, and I will get a theory that has this kind of symmetry. So let me mention an aside. So actually, this structure of this two group was first described by a mathematician called Huang Chuan-Xin, which was a student of Grothendieck, which was one of the first profs at IHS. And actually, he went to Vietnam during the war, to Hanoi. So he went to the north to give some lectures, allegedly while the bombs were falling. And then they just started talking, and then she did her thesis by exchanging 3 very long letters with Grothendieck, and then she went to France to defend it eventually. So it's pretty impressive what she did. But many years later, this has found its way back into physics. So back to physics. So here's the example of a theory that has this symmetry structure. So just take QCD, like actual ordinary QCD, and gauge baryon number. Okay, so QCD has a U1 vector symmetry, right? So if you think UN left, UN right, there's an axial U1 which is broken again by an anomaly, and there's a vector U1 which is just baryon number. Okay, so let's just gauge baryon number. So now we have a new photon in the theory. It's not the usual photon. It's a photon for a baryon number. So this is not the real world. But now this couples to the baryon current. So the baryon current in the Carl Lagrangian is this funny thing here. So it's conserved just for topological reasons. And it turns out that this U1 baryon has this kind of anomaly. Okay, so the U1 baryon has like a mixed anomaly with the usual chiral symmetry. So when I gauge it, I precisely engineer this two-group structure. Okay, so one can check that if I now look at the current algebra of the chiral current in the presence of this new photon, I will have this new contact term. Okay, so here this two-group is just the usual SUN left, SUN right chiral symmetry intertwined with the magnetic symmetry of this photon. Because okay, here you see that the shift symmetry is broken, so it's really the Bianchi identity that tells you that magnetic flux is conserved. So this is the conserved current. And there is indeed a double soft theorem which is modified. So the idea is that okay, now we have both the pions and the photon are Goldstones for this kind of group structure, higher group structure. And indeed, if we look at the sublinic double soft pion theorem, there's a new term here that depends on this new structure constant kappa, which was what I wrote as this FAB gamma, and it takes this very simple form. So it involves kind of this epsilon tensor with the polarization of the photon and the momenta of the soft pions and the hard particle, and then also somehow the complex conjugate of that. And it's a soft theorem that indeed mixes up pions and photons. Okay, so if I take two double soft pions and I have an external leg, which is a photon, it can turn that into a pion. So here we had an amplitude that has n, in the left-hand side, n plus 2 pions and n gamma photons. Right. So here, the soft factor acting on this is going to add a pion and remove a photon. Okay? And similarly, in this term here, we will have one fewer pion and one extra photon. So indeed, the promise is realized that somehow this term here is really like a structure constant that can mix up pions and photons. And this is what this soft theorem is telling us. Okay. Okay, so some comments about this soft theorem. So it just follows from the usual current algebra arguments. So we don't need to do anything fancy. We're using now the usual word identity with this extra term, and we just have to keep track of it in the proof of the double soft pion theorem. And this new term just gives rise to this new kind of subleading order soft factor. Okay. The fact that it appears at the subleading order, as I mentioned, is consistent with the fact that there's this extra derivative in the contact term. Okay. And it's not corrected by any loop effects or anything like that. Okay. So this we proved from current algebra. So we didn't do any diagrammatics, even though you could, in principle, at tree level, prove it from Feynman diagrams. This is really a symmetry-based proof, so we know that this is actually a true non-perturbative statement about this theory. And yeah, we've checked in all of three amplitudes up to 6 points that this soft theorem is satisfied. So let me give you a very simple example. So this is the amplitude with 4 pions and 2 photons. Okay, and so now I'm going to take the first 2 photons soft, and indeed this is the structure that appears. So this is what we expect from the soft theorem, that is related to the amplitude with now 3 pions and 1 photon instead of 2 pions and 2 photons. And and then when I plug in these amplitudes, indeed, I see that this is precisely the right thing. Because if I take 1 and 2 soft, I'm just going to kill these Mandel's here, and then these ones here. So so I get, sorry, which one time? Yeah. So one gets precisely this result. Okay, so I'm coming to the end. So hopefully I convince you that there's a new angle and all soft theorems using this language of one-form symmetry, which has become very popular in the last few years. And it makes it directly analogous to our understanding of pion. So we don't need to invoke any kind of asymptotic symmetries or anything fancy like that. It's just kind of ordinary conservation of currents in QFT. It's seems to also work for things like soft-gluons and gravitons, except that there the symmetry is only emergent strictly at weak coupling. So, and I think one can really think of gluons as gallstones, but just at zero coupling, which is where gluons actually make sense. So indeed, you can check that if you take Yang-Mills and you take the limit where the coupling goes to zero, then you have a bunch of these emergent one-form symmetries and kind of one per each gluon. And I suspect that the soft-gluon theorem can also be phrased, which is now a perturbative statement, of course, can also be phrased in this language of higher symmetries. And similarly for soft gravitons. So I think that's something which is worth pursuing. Is there a connection with the story at Scry? So, okay, there's some people in this audience that maybe like this perspective of asymptotic symmetries. Okay, here we have like Wilson lines that stretch all the way to infinity and pierce the celestial sphere. I suspect there's some connection to the way that people understand this soft theorem using that perspective. So I think it would be interesting to explore how to build a dictionary between these two ways of thinking about the problem. And I think our analysis also shows by example that these higher symmetries are likely generic emergent symmetries in these Lorentzian EFTs, like this kind of HUT, SET, all these kind of theories where we integrate a bunch of hard modes and we suppress certain processes are likely to enjoy the symmetry. So for instance, the kind of weak coupling, like ultra subsector of SET, I think will have these kind of symmetries. And they will impose some correlation functions on some constraints, selection rules and correlation functions of Wilson lines, and maybe soft theorem. So it would be interesting to also understand that. Also, whether there is a connection to statements about factorization using this symmetry language. And here I just presented one example of this kind of higher symmetry having an application to scattering amplitudes. But I suspect this is only the tip of the iceberg. So this is a very wide field. So there's many exotic symmetry structures that people haven't covered in the last few years. So I fully expect that there will be more applications, and that we know a couple of examples from the work of Lucia and friends and us, but I'm sure there will be more also in connection to these non-invertible symmetries. And I look forward to exploring that in the next few years. And with that, thanks everyone, also from my daughter, and